Alright, so now let's do part C. Using Parseval's identity, deduce the value of the sum from 1 to infinity of 1 over n squared. And remember that from part B, we have that the Fourier series is equal to this, and recall that, we can also rewrite this as the Fourier coefficient times e to the inx. Okay, so what does Parseval's identity say? So recall that Parseval's identity tells us that the sum of the squares of all the Fourier coefficients is equal to the integral of the square of the function, so kind of like the norm of the function. We can write this as, so the sum of squares of the Fourier coefficients is equal to the function norm of the function squared. We can also just write this as x squared dx. Okay, so let us deduce this. Now notice that because our zeroth Fourier coefficient is 0, we can actually rewrite this. We can split it down the middle and rewrite it as 2 times sum from n equals 1 to infinity of n squared. And again, this is due to the symmetric kind of magnitudes of the Fourier coefficients. And notice that since we're taking like the length, right, we're just multiplying this by its complex conjugate, which is just going to give us 1 over in times 1 over negative in, which is going to give us 1 over n squared, which is what we want. So this is equal to, oh, I meant 2 times squared. And now we see what we want, right? Which is pretty cool. Okay, so all we have to do now is calculate. So our function is x squared, that's always positive, so don't have to worry about the absolute value anymore. And this is just a pretty simple calculation. Right, so that's going to be 1 over 2 pi times 2 pi cubed over 3. This cancels, and we get that divided by 2. So when we divide by 2, what do we get? We get pi squared over 6, which tells us that the sum from 1 to infinity of 1 over n squared is equal to pi squared over 6, which is pretty cool. It's a pretty cool result. Okay, stay tuned for part D.